So we have the question where we have a parabola, an equation, and a line. The line is tangential to the parabola at this point, and we know that it passes through 0, 0. So immediately when we look at this question, we should be considering the fact that we have information, and we have to use this information. So we have the region R here, and the region S. Now you have to answer some questions. So the question 1 asks us to explain, to evaluate this integral, and then explain why the area of the region S equals that. And so I've just allowed you guys to do the integral. I mean, you just expand x, you expand this, so you get x times c and minus x squared, and do it individually. And then the point is that this integral shifted to the left by a units. So, and that doesn't change the area. So it's just shifting this graph. That doesn't change the integral, i.e. the area. And so therefore the area is going to be, so we get that it asks us to evaluate what it is, and the answer is c cubed on 6 when you just evaluate this integral. And therefore we just, it's c cubed on 6. And therefore, because we've translated it, I believe it's, we can just evaluate it and just see, I believe it's c cubed on 6. And because we've translated the region by c in this case is going to be the integral from 0 to b shifted a units that way. So it's going to be the integral from 0 to b minus a. So that's why you just get that out. So you just have to kind of say words like that. So the shifted will be this parabola going through 0 and b minus a. And so we just sub in b minus a for c. All right. So now the next question asks us to determine the line y equals mx, which meets the parabola tangentially as shown in the diagram that passes through 0, 0. And so we just have to use all the information we're given, and this is kind of like probably a straightforward thing for all of you guys, but we'll just say it quickly. So since it passes through the origin, what's the gradient of the line? The gradient is going to be where it meets the parabola, y0, x0, y0 and x0, change in y, change in x. The gradient is given by the derivative also at x equals 0, and because we know the equation, we can just find that the derivative is going to be a plus b minus 2x0. Now, we set these two things equal, and we get y0 equals this. Okay, so we have one equation for y0. We also have another equation. If we expand it out, we get y0 equals minus ab plus ab x0 minus x0 squared. Now we just have to set them equal, and we get x0 equals ab, and therefore x0 squared equals ab, and therefore x0 equals square root of ab. Note that x0 is positive, so it's not the negative square root. And therefore, we just sub in for m. We note that m equals a plus b minus 2 of x0 right here, and we can just get out the equation. Right. So, okay. So now you have to assume that a equals 1 and b equals beta squared. And given that the area of R is 2 beta plus 1, beta minus 1 squared on 6, show that the areas of R and S are equal precisely when this equation happens. This is not too tricky. We know that the area of S is equal to b minus a squared cubed on 3, which is going to be beta squared minus 1 cubed on 6. We then set these two expressions R and S equal, and we get this. which means when we just cross multiply by 6, we just get that. And now the key thing is to use the difference of squares. So beta squared minus 1 is beta minus 1 times beta plus 1. And so we can take this to the other side and factor out the beta minus 1 squared, and we just get this. And now it's a straightforward thing to check that that just matches the expression that they gave us. Okay, so now let p beta be the part inside here, because we know that the beta minus 1 gives a solution, of 1, right? So we can just forget about this guy and suppose it's not 1. So we want to know why there's a solution of beta greater than 1. And so we want to show that there is a solution of p where beta is greater than 1, right? So now we know what we need to do. We need to show, let's look at what p1 is. So when we evaluate p1, we find that p is negative. Okay. So now we know it's negative. So what we need to do is we need to find a value greater than 1 that's going to be, say, positive. And if p is positive at that value, then what we know is that at 1, it's going to be negative. At some later value, it's going to be positive here, and therefore it's going to pass through, the x-axis. Okay. So we just checked that p2 works. So we sub in 2, and we see that indeed you get 16 plus, 16 minus 8 minus 2 is positive, and that's voila, the solution greater than 1. And now it asks us to show that, without further calculation, show that for any a, there is a b such that the regions R and S are equal. And so the point is, we now have solved it for a equals 1, and so we want to produce a solution for all a. So how might we do this? We have to preserve the situation of the diagram. And so one easy way to do that is to just delete everything from the origin. So we start from the origin and make everything bigger, right? So we scale everything outwards. This tangent line remains the same. This parabola just shifts and gets bigger. And in general, what we know is that areas scale, when we scale by, say, a factor k, areas scale by a factor k squared. So if we start at 1 and we scale by k, R will go to area of R times k squared, and S will go to area of S times k squared. But because they're equal at 1, when you multiply by k squared, they'll still be equal. And therefore, after scaling by a factor of kappa, we can attain any value of a, right? So we know a equals 1, we can scale by kappa, and where kappa is like any value you want, and we get, we get every answer. So that's how you solve part B. It's about scaling the situation. How would you think of that? You'd want areas to stay the same. You want to control areas, but you also want to shift A. And a shift doesn't really work, right? Because shifting would shift the parabola, sure, it would shift it, but it would also shift this line, and then it won't pass through the origin anymore. So we need something that keeps that line at the origin, but still does something, and that thing could be, translate, delete or scale through the origin. And that's kind of how you would think of that.